to a place where we can actually kind of go back and look at limits. I mean, sorry, derivatives. Because before we've been looking at the function, at a function, like let's say f of x, and we've been looking at the derivative of that function, f prime of x. And now we're going to look at it purely analytically. Um, so we're going to look at finding derivatives of a variety of functions, right? Just in general, and we'll look a little bit more closely as we progress with the unit. Um, so we've been looking at them in terms of the slope of a line. Um, you can recall that derivatives are essentially the slopes of a function. And one form that we have seen is f prime of x equals the limit as h approaches 0 for f of x plus h minus f of x, all of that divided by h. And we call that the difference quotient, right? So slopes in algebra took on the form of change in y over change in x. And formerly, change in y, or delta y, over change in x, delta x, was what we traditionally refer to it as. And dy over dx, which is the notation for a derivative, is where that form came from. So Isaac Newton and Gottfried Leibniz, two figures in mathematics, they both focused on the instantaneous rate of change, which is what we focus on with calculus in general. Tangent lines thus far have led us to linear approximations. So they might ask you, what is the linear approximation of da 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 da, and you would be using that limit function, and it's also called linearization. But first, to kind of get an idea around derivatives, we need to look at what is common and what is not common. Okay, so like Leibniz, Lagrange, I've seen pretty much like in every math class after calculus, right? Euler, Newton, Euler, I've seen more like college professors use it, like Euler, and very rarely. And and I'd call it the lazy man's way of doing things. Now Newton, I never seen it except in like a course called A History of Math. Lagrange, I love Lagrange. I love Leibniz for different reasons. So Leibniz is pretty straightforward. It's just f of x, f prime of x. Like we would literally say, have this equation, f of x equals, I don't know, 3x plus 2, right? So here, f of x, another way they would say it is y prime, y prime prime, and y. Once we get past like 3, like we'll do, like they might have f prime prime, the third derivative. Once we get to the fourth, we start using numbers. Similarly here, we'd start using numbers. So just be cognizant of that. Now, with Leibniz was a DDX kind of man, and his would be dy of dx equals, that's dy over dx equals 3x plus 2. So wouldn't have this, it would literally be d dx of 3x plus 2. And what would that notation look like? What would that notation look like? So for the first derivative, this is the first derivative, it would literally be dy dx. So y is just the function. Y is just the function. So here, second derivative would be d dx squared. So that would like be like 3x plus 2, and we get the second derivative of that. D dx cubed, and it's not really a power, so I don't want you to think of it that way, but you would get continual derivatives. So And we haven't gotten to the point where we talk about these higher derivatives. But if y equals 3x squared, then y prime, this first derivative, would be 6x. Y prime prime, the second derivative, would just be 6. So we would keep going. That's how derivatives keep going, right? Euler, one of the most interesting and unique ways I've seen it was this notion of df equals df of dx. So if the function we're using here would be dx, uh, well, let's get the first one. So dx, um, it would be f of x, right? If I were to write that out, that would like be saying dx of 3x plus 2. Very similar to Leibniz in a way, but I'm going to erase that because I got to write into Newton's over here. But anyways, if you keep going, notation, big D, little bitty x right there, and a squared for that other derivative. And here's a function, D, and a 3 for that third derivative, and an x down there, and here's a function, the original function. Now, Newton was a dot person. He's using dot notation. So first derivative is y dots, second derivative, y dot dot, and so on and so forth. And it's just messy. This is messy. This is messy, but very useful. Leibniz is very useful. Lagrange is probably going to be your go-to. Lagrange is probably going to be your go-to. And Lagrange will come back up later on. I don't know why so many people get it mixed up, but this is the actual notation. And typically we're using Lagrange or Leibniz. Today we're going to be using Lagrange a lot. But before we move on, we want to kind of look at the derivative of trigonometric functions, how we get it, how we go about it, and what you'll need to know why we emphasize identity so much is particularly for these trigonometric functions, it's really, really helpful. So when we're looking at the sine of x, how might we first start to do this? And the reason these two particular identities come up is because of this notion right here. So what I'm going to do is write this out, the limit as h goes to 0 for sine of x plus h. And see in here, we're going to be replacing this alpha and this beta with x and h minus sine of x over h. All right. So particularly right here, this is where this identity comes in handy. So I'm going to go ahead and do that identity. So this becomes the limit as h goes to 0, and it looks like it could be so messy. I'm going to have sine of x cosine of h plus cosine of x cosine of h. Oh, did I write that right? Nope, I did not. I'm making stuff up. So when you start laughing at your own jokes and you realize they're not really that funny. So minus the sine of x. So all of that right there, I just exchanged for an identity. And I'm going to divide by h. So here's the part where I can start maybe pulling some stuff out, or I could figure some things out here. Okay. So if I plug in 0, for h, I get 1 right here, I get 0 here, and I get minus sine x. And what I end up with is sine x minus sine x over 0, and I'm still in a very, very bad place. Okay? Okay, so I had to get my lemonade. But what's unique here is we end up with these two. We can put those together and we end up with, if we factor that out, we end up with two unique limits. So we have, I'm going to split these apart as I can do that. The limits as h goes to 0, we have sine x. I'm not going to rearrange, but we have cosine of h minus 1. So looking at these two right here, over h, okay, plus this limit, cosine of x, sine of h. So, all right, so here we are. We can rearrange this. We can say that the limits as h goes to 0 of sine x of the cosine of h minus 1 over h plus the limit as h goes to 0 of cosine of x of sine h over h. Split those up at this point. That's one of the things we can do when we have these denominators like this, right? Now, I already know when I evaluate these limits, I can say sine x, I can bring that first function out and say limits as h goes to 0. And this part inside, if you don't recall, it's just 0. If you graphed it on a graph, it would just be 0. So we'd have the sine x of 0 right here, sine x times 0 plus, and then over here, if you don't, like what I'm looking at right here is this particular limit right here. And then I'm going to look at this particular limit right here. And remember I said anytime you see this, it's just going to be 1. So we can just accept that it's 1. So we'll have cosine, I'm going to rewrite it for you. The limit as h goes to 0 times that, and of sine h over h, right? This is just 1. So that's going to be plus cosine of x times 1. And I end up with, anything times 0, it's just 0, plus the cosine of x, and this limit is just cosine of x. So this is the proof for that. So the proof for cosine of x would be very similar in nature. We have a limit as h goes to 0. All right, so I'm just going to go ahead and break this out. Cosine of x plus h minus cosine x. I have over h, right? And we end up using this identity above. It's just the limit as h goes to 0 of cosine of, let's see, cosine of x, cosine of h, minus, and I'm just going to go ahead and see what we got here. Sine of x, sine of h, minus cosine of x. And we would do something different. We would do something similar, right? So we'd end up with, and I'm just going to go ahead and bring my cosine out. Well, you know what? Let me not skip steps. I told you guys not to skip steps. I'm not going to skip steps. So cosine of x, okay? Remember, I'm just factoring out from this portion and this portion, minus 1. And that's going to be over h. And then I'm going to go subtract. I'm just going to do a big bracket here so I have space. Sine x, sine h over h. And you can kind of see already, we're pulling out things that we have to accept, these axioms. This is just going to be 0, and this is just going to be 1. So this equals cosine x times 0 minus sine x times 1, and I get negative sine x. So if you ever get asked to prove this, you technically could. All right, I just wanted to go through that with you. We might do a tangent function eventually, but now we're just going to move on to doing these limits. I'm going to be using Lagrange style over here. So I might interchange between f prime of x and y prime, as well as f of x and y. Just note that they mean the same thing. Okay, so with constants, it's very simple. F, the derivative is just always going to be 0. Constants is very simple. Derivative is going to be 0. When it's linear, the derivative is always just going to be that number. It's going to be positive 1 here. Okay. When it's quadratic, it's 2 times whatever this number is in front. So f prime of x would just be 2x. And literally, you're just subtracting 1 for this exponent. Right here, f prime of x would just be 2 times negative 3x, and then 2 minus 1. This is just so it's clear about what's happening with this power right here, and it's just negative 6x. Polynomial in general, so we multiply times n, subtract n by 1. If you want to see it in action here, this is my 4 comes down. I say 4 minus 1, and it's just 4x cubed. I want to see it in action here. F prime of x, I say 5 times negative 1/2, and x to the 5th minus 1. That's going to be negative 5 over 2, x to the 4th. Knowing how it works will make it easier when we go into integrals. This cosine of x equals 2 cosine of x. Right here, we just multiply, that constant comes out. 3 cosine of x. Oh, something different. 3 cosine of 3x. So we retain the terms inside. Okay, over here, we just have negative sine x as our derivative. And make sure we note that that's the derivative here, okay, and not the function. Here, f prime of x, it's just going to be a negative 3. And don't forget, if it's inside, if it's a term inside, we retain it on the inside. Secant squared x, so it's going to be 2 secant squared x. So f prime of x, I'm just going to start with y prime, it's so much easier. 3 secant squared of 3x. And don't make it any harder than that. These are very easy. Over here, we have to do some extra stuff. I probably shouldn't introduce this too early. But terms inside, we literally bring it out to the front and multiply it. So 2. And this becomes 1 over 2x. And make sure I did that right. And the way we could prove it, well, we should go back and prove it at some point. We're not going to do it right now. Right here, f prime of x is just going to be 3 times 1 over x, that derivative right there, or 3 over x. Right here, this would just be 2e to the x. Right here, negative 3 e to the negative 3x. Make sure that's correct. And it is. Right here, we have, let's see, the number is a, so we'll have 2 natural log of x. We have negative 2 natural log of x. Right here, we would have 1 over x natural log of 2. 1 over x natural log of 3. And that's how that works. Pretty straightforward. So, so we're gonna leave that right there. There's more to that. There's more to that. And we're gonna revert back to our work with this tangent line. So it says for each of the following functions, find the equation of the tangent line to the graph of the function at a point. So first thing you're going to do is to get the derivative. Then you're going to get the point of tangency. Then you're going to get the slope. Well, we could actually do this first, but actually we should do that first. So we'll make that number 1, make this number 2. And then we're going to get the equation. We're going to use the equation y minus y1 equals m of that slope times 20 of x minus x1. Okay? And remember the point of tangency is just x1, y1. So here, let's go ahead and get our point of tangency. So that's f of negative 1 equals 2 times negative 1 minus 1. That's just negative 2 minus 1. And then we have negative 1 plus 1 squared. And that's just 0. So it's just going to be 0. Point of tangency here, POT, is negative 1, comma 0. And so I told you, you get a lot of practice with this. Now we move on to step 2, find the derivative. So derivative f prime of x. So what might be easiest for you is to just multiply this out. So 2x minus 1, multiply this out because we're not ready for this just yet. So 2x minus 1 times x squared plus 2x plus 1. And that's going to equal 2x cubed plus 4x squared plus 2x. And then we're going to have right here negative x squared, negative 2x minus 1. And my function is simplified, is just 2x cubed. So f of x equals 2x cubed. It's easier for me to do this way. It's probably easier for you to do this way. Right now, there is a much easier way, but we're not there yet. So let's go ahead and get this derivative. So 6x squared plus 6x. And remember, constants are always just 0. So we want to find f prime of negative 1, which is 6 times negative 1 squared plus 6 times negative 1. And we get 6 minus 6. And we get 0 as a derivative. So my slope for this tangent is 0. So I have that, and so now I can write this equation. Okay, I have 0 here. I have x minus 1. I have y minus 0, and I have y equals 0 as my tangent line. Interesting. So here, let's make sure this is correct. It's just going to be alpha. It's just going to be alpha right there. So I'm going to go ahead and get the point of tangency here. So POT, okay, so G of 0 equals 4 sine of 0 minus 0. I should have picked a better one. Let's do pi over 2. Okay, and so it's an awkward looking number, but 4 times 1 minus pi over 2, and it's just going to be 4 minus pi over 2, or I replaced 0 with pi over 2 because I didn't like that there was 0. And That's going to be 8 minus pi over 2. Okay. So anyways, point of tangency here would be pi over 2, comma, 8 minus pi over 2. And I'm sorry if that confuses you, but I just changed the x value here, or the alpha value. All right, so let's get g prime of alpha. Oh, I can see why I did 0 now. You know what? Let's go back and do 0. It looks simpler. I'm so sorry. I'm so sorry. I can't help myself. But keep in mind that a is just there. So g of 0 is just going to be 0. So the point of tangency is 0, 0. Now, g prime of a is going to be 4 cosine of alpha, and minus 1. 4 cosine of alpha minus 1. So I want to find a slope. So g prime of 0 equals 4 times cosine of alpha of 0 minus 1, and it's just going to be 0. It's going to be 1 times 4 minus 1, or 4 minus 1, which is 3. So here's my slope. Here's my slope. Okay, so I'm going to write my equation. Y minus 0 equals 3 times x minus 0. And I get y equals 3x as my tangent line for this particular equation. So not hard stuff. So here, f prime of x equals 3, negative 3 sine x. Point of tangency here, f of pi equals 2 plus 3 cosine of pi, and that's 2 plus 3 times 0, or just 2. So have my point of tangency, which is pi 2. Get my slope here. It's negative 3 sine. Oh, wait. That's a 1. That's a 1. So 2 plus 3, that's 5. My bad. I get those mixed up because I move too fast. So the sine of 0, the sine of pi is actually 0. So the slope is 0. Tangent line, y minus 5 equals 0 times x minus pi, and it's just y equals 5. Over here looks mighty complicated, right? But point of tangency, we'll go there first. We get 2 times 2 over the square root of 2 squared, and I get 4 over square root of 4, and I get 4 over 2 equals 2. So point of tangency here, 2, 2. All right, now for this, you could simplify this. It looks like it's complicated, but it's really not. So h of theta equals 2x over x. The square root of x squared is just x. This cancels. H of theta equals 2. H prime of theta equals 0. So you can't even evaluate it. There's nothing there. It's just that y minus 2 equals 0 times x minus 2, and it's just y equals 2. So very simple stuff there. I should have made harder problems. Just finding horizontal tangents or relative maximums and minimums. At what values of x will the function f of x equal x cubed plus x? So you're just finding the zeros. You're just finding the zeros of the derivative. So when I see this, it tells me that I am finding zeros of the derivative. That's basically all I'm doing. So I get the derivative, 3x squared plus 1. Find the zeros for this. So I just set that derivative equal to 0, and I solve for those numbers. I subtract 1 on both sides. I get 3x squared equals negative 1. I say x squared equals negative 1 over 3. I take the roots, the square root of both of these, and these are imaginary, so they're going to be up. There actually is no zeros here. And, well, these are imaginary. So that this function probably doesn't have a maximum or a minimum. So this equals the square root of negative 1/3. If you take the radical of both sides, right? Um, anyways, so imaginary f of x may not have maximums or minimums. Okay, so at what values of x will the function f of theta equal theta, theta, and we want to stay within the realm of 0 to 2 pi here. So we don't want to expand out because that repeats. So f prime of theta equals 1 plus cosine of theta, right? So set that equal to 0. And I have cosine theta equals 1. So you could take the inverse of each side, right? But I know that in order for theta to equal 1, then it must equal 0, 2 pi, or any even number here, any even number pi, where n belongs to all even whole numbers, and you literally could just keep it to this right here. All right. So basically, at what values when x equals 0 and when x equals 2 pi, or any even number pi. And I think that is all she wrote for that. Not a lot of hard stuff there. But yeah, just do the derivatives, get the practice in, and that's all I got for you guys.